Come on in, everyone. Feel free to ask me any questions while we're waiting for everybody else to get in.
Professor, real quick, I'll ask. I missed lab today in person. I misunderstood your emails. I sent you an email. I just want to let you know in person, or I guess in Zoom.
Okay, no problem. It's you're allowed to miss one. So I mean, in other words, I drop one absence, I also drop one lowest lab grade, so that should take care of that.
Okay, super. That's awesome. Thanks.
No problem. Sorry about the last minute changes and getting the information to you after 5. That was my fault too. So, uh,
Good afternoon, Mr. Younger.
hey,
I
how's
just
it
want to let you
going?
know it's Darren, Ella, and I on one Zoom.
Gotcha. I see y'all in there. Y'all over at the library?
Yeah,
Cool. That's a nice space, ain't it?
It's a
yeah,
very nice
definitely.
space.
So just want to let you know for attendance purposes.
No problem. Thank you. I see Darren and who's the other person?
Ella.
Ella.
Oh, Ella. Gotcha. Guy. No problem. Appreciate that.
Which is actually kind of funny because I'm in 210. I'm in 210, not too far away from them.
Yeah, I saw you at the front desk. I figured you had your own room.
I did.
That's cool. All right. Well, I've done the calorimetry part of chapter 19. I didn't work an example like making ice. Uh, so I'm going to go ahead and do something like that now. And then I'm going to jump into completing chapter 19. You guys are supposed to have a test next week during lab, if I remember correctly, because y'all meet on Wednesdays. And next Wednesday will be a week from today. So that'd be January 32nd. That sounds good to me. January 31st. Yeah, that's good. So January 31st, yeah. Yeah, that's just one. Okay, that's cool. Just making sure. All right. Anyways, so I wanted to just do that before we start on the rest of the material, which mostly is about the first law of thermodynamics. So I'm going to go start off by sharing my screen. Does anybody have any questions before I jump into that? Okay. Remember, this is always a time where you can ask me questions about homeworks and all that good stuff. We're going to move on and start covering new material, and it depends. I definitely already put out test 1, the online test, and that's just on 17 and 18. But there the face-to-face test that happens in the lab will maybe be at least the first half of chapter 19, but it could in principle be just 17 and 18 again. That's what I'm currently leaning towards. So I just want to let you know that that's a possibility. Make sure you guys get your online test done by Sunday at 11:59 p.m. So it's been posted. I posted it. I think I posted practice test day before yesterday and posted the test itself yesterday. So that should all be available to you. What we're trying to do is this is along the lines of calorimetry. And oh, another person came in. What we want to know is how much energy must a freezer remove from, let's say, whoa, Nelly, 3.00 kilograms of ice, or excuse me, of water, I should say, at 20.0 degrees Celsius to make ice at negative 10.0 degrees Celsius. So that's our question. And hopefully everybody can read that cursive. If not, it's a good time to practice. And of course, I'll read it to you again. That'll help. So how much energy must a freezer remove from 3.00 kilograms of water at negative, or excuse me, at 20 degrees Celsius to make ice at negative 10 degrees Celsius. So here's our solution. Remember, we have two mechanisms by which heat can be used. One mechanism is in the mechanism of changing temperature, and that one we know is given by Q is equal to MC delta T. I'm usually pretty pedantic in that I always try to make that C lowercase because the uppercase C is supposed to be for non-specific heat. So when you talk about heat, uh, it would be non-specific, but if you talk about heat, which is measured in like calories per gram or calories per mole, that's supposed to be a specific heat. So I use a lowercase c. Your book sort of basically looks like it uses capital C for everything. So be careful with that. The other mechanism was the Q is equal to ML. And again, my paradigm is that Q lost equals Q gained. So that's what I use rather than delta Q equals 0. So what I'm going to do is what I realize is the water is going to lose heat. And that's going to have to come from the freezer specifically. So the water losing heat will be mass of the water times specific heat of water times delta T of water. And this is only in going from 20 to 0. But then we're also going to have to freeze it. So that'd be the mass of the water times the latent heat of the water. And then it's going to have to do the mass of the ice times the specific heat of the ice times delta T of the ice, which is supposed to be from 0 to negative 10 degrees Celsius. Now that's supposed to be Q gain. Now all that heat, of course, that's been taken out it'll actually be ultimately pumped into your outdoors. So I'll just say Q freezer. Okay. And that's all we're looking for. Notice all of them are going to be positive quantities of energy because that's when I use this Q loss equals Q gain, all the terms have to be positive. So as I start to write this out, I'm going to say 3.00. I'm going to leave off the units just for convenience. We know that that's 3 kilograms, by the way. So I know that the specific heat of water is 4,186. Shoot, I wrote a J for 6. That's not cool. I do have some letters that I associate with numbers, like the number 4 is a clear F to me, and I don't understand why. But anyways, that unit, of course, should be in joules per kilogram Celsius degree. And then this goes to a final temperature of 0, but because each of the terms has to be positive, I want to do 20.0 degrees Celsius minus 0.0 degrees Celsius plus 3.00 again. Now I need the latent heat of fusion for ice, which in this case is 3.33 times 10 to the 5th. And that's joules per kilogram. So you see that gives you joules as well. And then the mass of ice is also 3.00 kilograms. However, the specific heat of ice is actually half or about half of the specific heat of water. It's 2100. And that's joules per kilogram Celsius degree. And then now we're going from 0 to negative 10, 0 being higher. So I'm going to put the 0 first minus negative 10.0 degrees Celsius like that. And all that's equal to Q freezer. So ultimately I say Q freezer is equal to, now we'll start combining terms. I'm going to say 3 times 4186 times 20 is equal to 251,160. So I'm gonna call that 2.51. And actually that's one extra sig fig. Yeah, that's one extra sig fig. No, that's actually the same number of sig fig. So I really should do one extra on there. So I'm gonna say 1, 2 times 10 to the 1, 2, 3, 4, 5 joules plus 3 times 3.33 e to the fifth gives me 9.99. That's the extra sig fig times 10 to the fifth joules plus 3 times 2100 times 10. That gives me 6.300, one extra sig fig times 10 to the fourth joules. Okay. So I could actually write this as 2.512 plus 9.990 plus, if I want to make all of them times 10 to the fifth, I'd multiply the 10 to the fourth by 10, but then I got to divide the 6.3 by 10 as well. So that'd be 0.63. All of that times 10 to the fifth joules, and that's the way you do addition of scientific notation when you don't want to use a calculator. You just make sure they all have the same power of 10, and you do that by multiplying by 1 if the power of 10 doesn't work, isn't the same as the other ones. In this case, it was a power of 10 being 4. So if I multiplied that by 10, that would make it 10 to the fifth like the other ones, but then I'd have to divide it by 10 or else I'm not multiplying by 1. So when I add 2.512 to 9.99, I actually get I actually get 12.502. So 12.502 plus 0.63 gives me 13.132. So I'm going to say 13.132 times 10 to the fifth joules is what the answer should be. Of course, I'm only supposed to have 2 decimal places after it. So that, and these are all addition. So that means only 1 sig fig there. And this, of course, also interprets to 1.313 times 10 to the, now I had to divide the 13.132 by 10 to make it 1.3. That means I have to multiply the 10 to the fifth times 10. That makes it 10 to the sixth. So that should roughly be what it is. Now I'm going to do it with the calculator just because there's a high probability that I made some arithmetic mistake. I make a really lot of bad mistakes in adding and subtracting. So I'm going to say 2.512 e to the fifth plus 9.99 e to the fifth plus 6.3 e to the fifth, or e to the fourth, excuse me. That gives me 1.3132 times 10 to the 1, 2, 3, 4, 5, 6. Yep, I got it right. Woohoo! Mr. Younger does arithmetic. All right, any questions on that one? Notice how I had to break up the water transition from changing the temperature of aqueous water, i.e. liquid water, from 20 to 0. That took one specific heat. Then from 0 to -10 took an entirely different specific heat because it's no longer water. It's still H2O, but in this case it's solid. And it turns out that in its solid state, the specific heat of ice is lower than the specific heat of water. So actually, a igloo is not quite, if you actually imagine a cartoon igloo made out of ice blocks, okay, that's actually not as insulated as a water igloo or a bubble would be. So if you actually were able to make a structure that was shaped just like the inside of a sphere, and then another structure that was shaped just like the outside of a sphere, and the difference in radius of the two is exactly the thickness of the blocks that you use for the igloo, and you, instead of filling it up with igloo blocks of ice, you fill it up with water, you would have almost twice as much uh, insulation from the water than you would from the ice. But anybody have any questions on that? All right. So just remember also, that's one of the rules that we sort of learned is by that diagram I drew last time. We see that, water will change temperature, change temperature, change temperature, change temperature until it gets to the change of state temperature, which at 1 atmosphere is essentially 100 degrees Celsius. But at that point, the temperature stays the same until all of the water has boiled away. That's the use of a boiling water. So, for instance, when you take spaghetti noodles and you throw them in a pot of water and wait for them to come to a boil, or you do that with other types of foods, what you're doing is giving those other types of food a long period of time subjected to a very fixed temperature that exceeds the quote unquote dangerous temperature of the food. Like if you're actually wanting to cook a steak, well, let's not say a steak. Let's say we want to cook a pork chop, because in principle, there's not really a well, there's some danger in undercooked beef. Obviously, it's a lot less danger with a steak than it is with hamburger, because hamburger is actually processed, and there's some probability that some of the ooey gooey could have gotten on the hamburger, and there's a lot less probability that some of the ooey gooey could have got into the meat. So it's a lot less safe to eat processed hamburger at not fully cooked than it is to cook a steak not fully cooked. In fact, there's literally been people eating not only raw steak but raw hamburger for decades and not suffered consequences. But there's been a lot that have been eating raw hamburger and suffered consequences. Okay, so if we did it with pork, we know pork has to be like 175 degrees Celsius. Do not, you need to Google that. Don't trust my memory on that, because I Google it every time I do it. But if you need the water, if you needed the ham or the pork or the pork chop to get an internal temperature of 175 degrees Fahrenheit, you could obviously put it in a vat of boiling water, and that vat of boiling water is going to be at 212 degrees Fahrenheit until all the water's gone away. By throwing that meat in there, you allow it enough time for it to reach equilibrium with the water, then you've cooked it all the way to 212 degrees Celsius. You don't really want it that cooked, because then you'd be eating like shoe leather. But you could take an internal temperature thermometer and check the core of it at the thickest parts, and that would allow you to eventually get to the 175 using the 212. That's what the sous vide is supposed to be for. So if you're, in the process of pushing out a buttload of steaks, it might be wise for you to have what they call a sous vide. Again, I don't know how to pronounce that. It's just a word I've seen in a machine I've seen on Amazon. But it basically, you could set the temperature, say, to the temperature of rare steak, and you set that temperature there, which let's say it's 110 degrees Fahrenheit. You set it to 110. You go ahead and flavor all your steaks. You put salt on them. You put garlic on them. All that good stuff. You put any kind of rub on it you want. Then you put them in individual Ziploc bags and get as rid of much air as possible. Then stick it in this water bath that the sous vide is, and then that water bath will keep it at 110 degrees Celsius, or 110 degrees Fahrenheit. As long as you keep the meat in there, it will stay. It will eventually reach 110 degrees Fahrenheit, and all the meat will be 110 degrees Fahrenheit. So if someone comes in and orders a medium rare steak, you just pull it out and then you throw it on the skittle or the skillet, throw it on the skittle. You throw it on the skillet and, just basically uh, cook each side. In other words, finish it off by frying the outside edges and then serve it to them. If they wanted it rare, you'd throw it in for a split second, get the outside kind of browned, get each of the edges kind of brown, then flip it over and get the other side browned. So that's a very helpful thing in everyday life. It just gives you a set temperature. Or if you wanted to get an object to a temperature, let's say this aluminum block, if you wanted to get it to a temperature, this is not an easy thing to determine the temperature of, right? It don't have a little booty hole or mouth hole for you to stick a thermometer in, right? So you can't really do that. In other words, the one thing we can do is shine an infrared camera on it, and that only gives you the surface temperature. There's ways you can use infrared to do other things, but the main thing is that just gives you the surface temperature. But what you can do is you can throw this block of water in a pot of boiling water. And since it's aluminum, it's a metal. And since it's a metal, it's a conductor. And since it's a conductor, it actually allows heat to enter and leave very easily. So in a very short period of time, it would reach equilibrium with the boiling water. And as long as the atmospheric pressure wasn't crazy high or crazy low, you could say, okay, well, this metal block is now 100 degrees Celsius or 212 Fahrenheit. And that's just another way of finding out a temperature of something. Of course, you had to set it to that temperature. But anyways, any questions on that? All right, your book does a couple other problems. It does problem solving for calorimetry. It tells you a nice system to go by. It then solves the problem of determining latent heat. Those are all good examples, and I want to remind you guys that when you're taking physics, we sort of expect you to master every example in the textbook on every subsection that we are going to test you on. So that's something you want to keep shooting for. I'm going to go from here and therefore not show you all those examples because you have those examples to work. Plus, you have all my examples online. Plus, you have the examples I make up in here. So you have plenty of opportunities to see various examples. But the holy grail is, can you write down an example from your textbook, close your textbook, and then solve it? If you can, then you've mastered that particular example, and you should get that way on all the examples in the relevant sections. And once you get to that point, that's a good time to start doing your homework. Okay. If you haven't quite done that, that's also a good time to start your homework because sometimes the easier lower level homework problems can help you get to the point where you understand that example. So it's sometimes a give and take. Sometimes you do all the examples and then work on the problems in the end of the chapter. Our homework's what we do. Or you can do it where I try to work one of the examples and I got stuck. So I found that subsection in the textbook and tried to work some of the odd problems in there in hopes that I would be able to do those easy ones and then come back and do this example. So that's what you should be doing day in and day out and trying to figure stuff out. Let's move on. I will remind you that the latent heats can be positive or negative, but by using my Q loss equals Q gain, I never have to deal with thinking about that. But for the record, if you're going from a solid state to a liquid state, you can imagine the individual atoms or molecules are in that little lattice, and that little lattice means that there is uh, a pull between one atom and its neighbor, or between one molecule and its neighbor, and that pull is what's keeping them in that lattice. And in order for you to break that lattice so that the molecules or atoms are just sort of rolling around each other as opposed to being in that rigid structure, you have to break the energy barrier that holds them together. So yeah, you have to put heat in, and Q is positive for going from a solid to a liquid. If you're going from a liquid to a solid, you have to take heat out. Okay. Also, if you go from a liquid to a gas, the liquid has the individual molecules or atoms again attracted to one another such that any two molecules can spend a good time around each other before they move on to the next, but they can't completely break loose where they're not close to any of them. So you have to break that amount of energy, and therefore you have to put energy in again. So that's again a Q positive in going not only from solid to liquid, but in going from liquid to a gas as well. One special case of that is evaporation. So, for instance, when we're exercising, running, whatever, we build up a sweat. If it's really humid outside, it doesn't help us that much because the air is very nearly saturated and cannot absorb any of the water that you've got bubbling on your body or beating on your body. So, what happens with evaporation, if it's not that humid, is that it can actually help you because what happens is it takes the heat from your body and from the other water on your body, i.e., the sweat that's gotten on your body. It takes heat from that to allow the fastest end of the Maxwell distribution. Remember, Maxwell distribution gives you the range of velocities for that the molecules will have in a substance. The ones at the higher end, way above the mean, they will actually escape and in some sense like boil away, but it's boiling away at a temperature that's lower than the boiling point, so we call it evaporation. That process, stealing heat from your body and stealing heat from the water that your body put out, all of that results in you cooling down and the water that is sweat evaporating. Okay. So that's something else that's helpful and should be something that you understand from a conceptual standpoint. I've highlighted a various sentences in here in the book, and it's my understanding that those are supposed to be shared with you, so you'll see where that is. I'm going to go on to kinetic theory and latent heats. I just discussed that to some extent. By the kinetic theory, we learned that there's a certain average speed. We found that the root mean square speed of an individual molecule was 3 kT over m raised to the 1/2 power. It's 1/2 of 3k or square root of 3 kT over m, where m is the mass of the molecule. That's the root mean square velocity. But the Maxwell distribution that we worked on showed you a way to calculate what fraction of those molecules are in between the velocity v and v plus dv. And therefore, if you integrate from 10 degrees Celsius, or excuse me, from 10 meters per second to 100 meters per second, it'll spit out the number of molecules that have that speed. And what you'll find is some of them have enough speed to escape the surface tension of a sweat ball, and therefore they can evaporate. Darren has a question. Yes, sir.
Mr. Unger, I had a quick question about the root mean square formula.
Right.
When we were doing practice problems, we encountered one that had, instead of kg, it was kg over mole. And we found a new formula online, which basically, instead of kt, it used capital R times T. Would there be another way of getting from the 3 times kt to that formula, or another way of solving it without needing both of them?
Yeah. So what I told you, for instance, like specific heat is something that's measured per mass or per unit mole. So yeah, anything that you see that normally has a per kilogram or a per gram could also be per mole or something like that. And the big thing that relates them is if you multiply Avogadro's number times the Boltzmann constant, which is 1.3807 times 10 to the negative 23rd, that gives you the ideal gas constant, the 8.314 that we use. So
Okay.
that's the relationship between probably the expression you found and the expression that we gave in your book.
All right, thank you. Yeah, I think that's what Darren did. I just wanted to make sure that was the another path.
Yeah.
It was another
In
path.
fact, in our last notes, if you're looking at this right now, I think I can pull this up. Let's see. I think it was here. Yes, I gave you, for instance, that formula right there where it says E 3/2 NKT and then 3/2
Oh,
NRT. So
yeah, okay.
yeah,
I see.
that's probably where it came from as
Okay.
well.
Yeah, I missed that, or I didn't write that NRT one in my notes. Thank you.
No problem. No, that's good. It's and this stuff's a little confusing. They got so many different ways of looking at it, and you're black boxing a little bit, so that's a bit of a problem. We're gonna go on to the first law of thermodynamics. And what I want to tell you about the first law of thermodynamics, let me go ahead and cordon this off, if you will. It won't let me switch to black for some reason. It's just being a butthole. Ah, it won't let me do anything. Oh, I see why. I think the end of my pencil tip. Yeah, that's exactly what was wrong. The end of my pencil tip had come unscrewed, so it was acting like it doesn't know anything. All right. So this is the first law of thermodynamics. Whoa. So what we learned last time and what I've been talking about a little bit since we started chapter 17, in fact, was that the internal energy of a sample, that could be a sample of gas, a sample of metal, a sample of air, whatever. It could be an object, it could be a chunk of iron, for instance, or whatever. The internal energy is the sum total of all the energies of the molecules or atoms making up the object. That's the total internal energy. Okay. And you probably, by thinking about that specifically, let's say our system is this little aluminum block again. So if I went in and checked out every little, this is a case where I got a pure element, so they're all atoms, so I don't have to talk about molecules. But if I went and found out all the energies that these individual atoms had, and I wrote them all down and then added them all up, what I would get is the total internal energy of this. Now, if I was assuming this was an ideal gas, which clearly not a gas, okay, but if I brought it to such a temperature that it became liquid and then kept on doing it, raising the temperature until it became a solid, I mean a gas, then I'd be dealing with an ideal gas. And if it was an ideal gas, then I can't even think about the molecules or atoms in this case as having parts, because the nature of an ideal gas is the atoms or molecules are infinitely hard little microscopic balls of very small diameter. So their diameter is supposed to be smaller than the distance between them and all that good stuff. But in reality, things are made of atoms, and atoms are made of things, and molecules are made of atoms. So there's energies associated with those other little things, energies associated with what orbital the electron's in. So if the electron's in the outermost orbital that's not completely full, but it's the lowest one it can get to because there's no openings in the other ones, then it's in its ground state. If it bumps into another atom, that might force the electron to gain enough energy to jump up to the next state, in which case the atom is now excited. And in that excited state, it has more energy than it did in the other case. So that's what happens when you bring in the complexities of matter beyond just treating them as infinitely hard little metal spheres, if you will. Okay. So the first law of thermodynamics talks about all of that. We're going to talk about the first law of thermodynamics in terms of ideal gases, but in terms of things in general. So if you picture this as our thing with a certain amount of internal energy, you can immediately say, okay, well, what happens to the internal energy if I start by taking this block of metal and suspending it over an open flame? So if I'm suspending it over an open flame, the open flame is obviously hotter than the object. So is anything going to flow from the fire to the object? Go for it.
Yes.
I guess only in the weird situation where like you got one of these like plasma torches that are like cold to the touch.
Oh yeah, yeah. Except for those weird situations, yeah. Or yeah, like liquid nitrogen or something like that. It feels like it burns you even though it's cold. But yeah, that is a special point taken into consideration, Jerry. So yeah, you always need to know that. But sometimes we find that the behavior is the same. For instance, if you freeze a wart off with liquid nitrogen, it will blister just like it was burnt. So that's another process. But in that case, the liquid nitrogen was acting as a super cold source. And what actually, I say source, what actually happened is your body heat was summoned to the location at which the liquid nitrogen was applied. And a vast amount of heat went through your skin at that spot to cool off the liquid nitrogen. And heat flowing through your skin is the very definition of what causes a blister. So yeah, that's how that still worked out. I think that might have been not Darren. Yeah, maybe it was Darren, but it might have been. I think it was Elijah was getting ready to say something. You were saying yes, Elijah, but do you know what that is? What is that flowing from the fire to the sample?
I
Thermal energy?
I mean, yeah, I was gonna say like thermal energy or like just the heat itself, but I don't know if that's actually the answer you're looking for.
Yeah, heat itself is what I was looking for. Remember, the definition of heat is a flow of energy from a hot object to a cold object. Okay. And that's just anytime that happens, anytime a hot object is interacting with a colder object, the interaction is energy flowing from the hot object to the cold object. So what we would say is that if we increase the heat added to a system, that we would expect that to cause the internal energy to go up. Do y'all agree with that? Okay, so that's the first part of the first law of thermodynamics, that if you add heat to a system, it could cause the internal energy to go up. So, one, if heat, positive Q, is added to a system, the E internal of the system increases. And I say positive Q because that's the definition of when Q is positive. If you take and choose your system to be whatever part of the universe, like that block there, and if you say heat is flowing into it, then that's a positive quantity of heat, which could be measured in calories or ergs or joules or whatever. Now, let's consider another aspect of this. Let's imagine now that this block right here is our system. We already considered the case of hanging it over an open flame and heat flowing from the heat of the open flame into the solid. But what if I were to put an immense amount of pressure on this? Everybody knows that liquids and solids are essentially incompressible, but that's not a completely true. You can actually compress them. It just takes, uh, multi-million Newton forces to do such. So let's imagine us putting this in a press, like might be used in a blacksmith shop, and I start banging on this thing while it sits on a perfectly immovable steel object below, and this thing's being bang, 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 bang. And slowly, this dimension, which was like 5 centimeters or 4 centimeters, becomes smaller and smaller. Okay, then what I've done is I put work into the system. I did work on the system. Do you think that causes the internal energy of this to increase or decrease?
Increase.
It is going to increase. And in case that wasn't crystal clear, you can think of it this way. All of those atoms and molecules in there are vibrating around, and they have this dimension of the block that they're free to move in. If you force it to move in a smaller direction, in a smaller dimension, then what's going to happen is those blocks are going to hit the walls a little earlier and therefore hit more frequently, and therefore more collisions per unit time means more average kinetic energy. So it's probably going to increase the temperature. So that's one way of thinking about it. It could also increase the potential energies regarding the distances between the individual atoms as well. So it doesn't all have to go into temperature, but it has to contribute again to an increased internal energy. So two, if work is done on the system, and I'll say positive work, the internal energy of the system increases. Okay. So putting those together, the conclusion you might reach is that the change in internal energy, again, I'm telling you, we use E with a subscript INT for internal energy instead of U. That is going to be equal to Q, the heat added, minus W, the work done by the system. Now, we could make this into an equation for infinitesimal changes, and if we did that, it would become dE internal is equal to d bar Q minus d bar W. Okay, both of those are the first law of thermodynamics. And you'll notice I've got a D in front of the E internal in the second version. So I mean, literally, that's a differential. That means there exists some function E internal such that dE internal is the partial of E internal with respect to X times dx plus the partial of E internal with respect to Y times dy plus the partial of E internal with respect to Z times dz for whatever variables that the internal energy depends on. The key point is the variables that the internal energy depend on are called state variables. And state variables have an actual possible differential. They're things that an object, they're properties that an object can have, like volume or pressure or temperature. So it's perfectly fine to say dV or dP or dt because they are state variables. But you cannot talk about how much heat something has because the heat is a flow of energy from one object to another. And you can't talk about something as if it has a certain amount of work because work is the exchange of energy by mechanical means. So get those two definitions. Heat is the exchange of energy by difference in temperature, whereas work is the exchange of energy by mechanical means, right? So those two are not state variables, so you can't write a D in front of them as if there's a partial of Q with respect to X times dx plus a partial of Q with respect to Y times dy, because Q is not a state variable and neither is W. So technically speaking, you can't just integrate that d bar Q because that d bar Q really means an infinitesimal amount of heat added, and that d bar W means an infinitesimal amount of work done on the system. Okay, so notice this is about work done on the system. So I will write here Q equals heat added to the system, and W equals work done, and here's the key word, by the system. Because of that, Q is less than 0 if heat is extracted from the system. In other words, if you put your block up against another object that's colder, then obviously heat's going to flow from the block into that other thing, that colder thing. So you'd have a negative Q, and W is less than 0 if if work is done on the system. Okay, so a typical system, better than this block, for instance, is to think of let's say an orange juice bottle with air, with a gas in it. Okay, now you take that the top of that bottle and cut off the part where it turns into a neck, and then we just have basically a cylinder shape. And now we put a plastic piece or a wood piece or something inside of there that's exactly as big around as the opening in the cylinder of the orange juice bottle, and then that thing acts like a piston. And we could do some stuff around the edges of that plate to make it a little bit better sealed. But if I now take that plate and push down, causing the plate to go further and closer to the bottom of the orange juice bottle, then I'm actually doing work on the gas. And that kind of work would be called a negative work. The Darren group has a question.
I just want to clarify, a system, like when we're referring to a system, it can be anything, like for the example of the block being suspended over the flame is also considered its own system.
Ah,
Are
that
we,
all depends. You can choose the block and the flame to be the system. And then there would be no delta Q, because
okay,
if it was in a container that was sealed so that no heat can go to the environment, then the Q would be 0. It wouldn't count the Q leaving the fire going into the block, because that's part of the system. But if you counted the block as a system and the flame as its environments, then you'd say, oh, there is a Q in
okay,
the equation because heat is flowing from the environment into the system.
okay. So in most cases, we're picking its environment and then the system itself in most.
Yeah,
Okay.
in all cases, you get to choose the system, and through experience, you learn what's the best system to pick on a case by case basis. Sort of like we did with Newton's second law. If you had a typical thing, is you could imagine a kid pulling a little wagon, and then you could have a string tied to the back of that wagon and another wagon be attached to that. If you treated the very back wagon as the system, then that system has an external force acting on it, specifically the tension in the string. And you could use that to solve for the tension in the string by measuring the acceleration of that last wagon. However, if you treated the system as the baby plus the first wagon plus the second wagon, you'd never be able to solve for the tension between the first wagon and the second wagon, and you wouldn't even be able to solve for the force that the baby puts on the front wagon, because again, that's part of the system. So that's how this all works. Is you got to figure out what you're wanting to know, and then what system best exemplifies that. Does that help? All right.
Yes, thank
So
you.
you're welcome. So that's the first law of thermodynamics. Your book does talk about that d bar Q and d bar W stuff. Uh, you might like their definition or their explanation a little better. Doesn't matter. Over time, you'll get used to it. I didn't get it when they first told me it, and I suspect some of you aren't going to get it right now, anyways. But you will eventually get it. So let's look at an example, and the example is going to be, let's say. Whoa, Nelly. I hate it when I leave it on the special drawing tool. Let's say 3,000 joules of heat is added to an ideal gas, and 2,000 joules of work is done in compressing the gas in its cylindrical container. And I'll say, oops, I'll say via a piston. What is the change in internal energy of the system? Okay, so 3,000 joules of heat is added to an ideal gas, and 2,000 joules of work is done in compressing the gas in its cylindrical container. What is the internal energy of the system? So let's do solution. The solution is delta E internal is equal to Q minus W. Q equals heat added. And W equals work done by the system. Okay. So what that tells us is Q for this particular problem is what? Positive or negative, and what's the number?
Positive 3,000.
Exactly, positive 3,000 joules. And W is equal to what?
Negative.
Yes, the W is going to be a negative, and that one will be 2,000.
That's gonna be plus. Well, because it's being done on the system.
Meaning it's W minus Q still, right? Not plus Q.
Well,
Are
no,
you getting that, Elijah? He's
Well, no,
right. It's the W is negative because in physics we use a minus W instead of a plus W like you do in chemistry. We use a minus W because we care more about the work done by the system, specifically steam engines and engines in general, internal combustion engines, were what we were looking at. So we tended to call work positive when it was work done by the system. In other words, when a gas expands, that's work done by the system if the system is the gas. In this case, the gas was compressed, so that's work done on the system, and therefore it should be negative.
okay, so like,
it'll end up being 3,000 plus.
no, I understand like the math of it. I'm just trying to wrap my head around
But
by
why?
like the work done by versus work done on, because I thought if we're considering the system the gas, isn't the compression working on it then?
Yes, and that's the whole point. The compression is working on it instead of it working on the environment.
Okay, so I just flipped it around. Okay,
Yeah. Yeah. And remember, you specifically answered this question before when I said, imagine me putting this thing in a big vise or something or a press and compressing it down. You made the argument that me putting all that work into this system, which is the little block, actually increased the internal energy. Since I have a negative in front of the W, you would have expected that to become a positive quantity. And the only way that could have become an increase in internal energy is if the W was negative. Because a minus a negative is plus a positive. Does that make sense?
yes.
Okay. So what we end up getting is 3,000 minus negative 2,000, which is positive 5,000 joules. And that's that's the change in internal energy. Now, if it's an ideal gas, that basically means the internal energy is going to cause the temperature to increase, because for an ideal gas, an ideal monatomic gas, for instance, E is equal to 3 halves nRT. So if you change the number or the temperature in an upward fashion, you're going to get an increase in internal energy. That also means if your internal energy increases, the temperature must increase. So that would suggest all of this would require the temperature to increase. Make sense to everyone? Now, in practice, and I've mentioned this numerous times, maybe it never set with you that well just because it was so generic of a statement, but the first law of thermodynamics is a conservation of energy. So, dang it. The first law is a statement of conservation of energy. So if we go back to what James Prescott Joule taught us, that there's a mechanical equivalent of heat, then we might say the first law of thermodynamics is delta K plus delta U plus delta E internal is equal to Q minus W. And that's actually correct as well. Okay, but that does use a different version of conservation of energy than I used to use. Remember when I taught you guys conservation of energy, I said K initial plus U initial plus E loss plus work in, all that other stuff equals K final plus U final plus blah, blah, blah. This is the one where delta E plus delta U is equal to 0. That's what they're using there. So let's try another example here. So here's an example. I think I'll borrow.
Professor, on
Yes.
that last thing that you had, where you had the delta K
Mm-hmm.
is plus what was it? The delta K plus the delta U plus the delta int is equal. So I thought we were talking about E internal was like all the energy, and then K and U were like, that's kinetic and potential energy. So like, can you explain that
Yeah,
little
I'm actually
equation
glad you
real
asked
fast?
that because that's an important thing to understand. The E internal, when I said that, so you have a system that might be a collection of gas in an orange juice bottle, and you survey the individual atoms or molecules in that and find out how much energy each of those has, and that's your internal energy. Now you also say, what if that little, volume of gas inside of that little orange juice bottle is thrown? Now you've got that whole mass of the system has a kinetic energy 1/2 mv squared as a result of its center of mass flying with velocity v. And in fact, if you threw it slightly upward, it would also have an potential energy given by m times g times the height of that system. Perhaps you'd calculate the center of mass of the little sample and then measure the distance between that center of mass and the ground height, and you call the ground height 0. That's where the delta U comes in.
All right, so that basically the first two terms are the macroscopic level that we're used to, and then the E int is the microscopic.
Exactly. That's a good way of putting it. Right? So let's try this example, and I think that'll make it a little bit more clear. And I'm more or less mirroring what your book did. Let's say a 4.3 gram bullet let's say leaves the barrel with a muzzle velocity of, let's say, 300.0 meters per second, enters a tree, and then exits with a speed of 200.0 meters per second. Whoa, Nelly. Where did the bullet's kinetic energy go? And how much energy was transferred? Okay, so that's going to be our question. So this is one where I'm trying to include the mechanical energies into my first law of thermodynamics. And we know specifically that that tells me delta K plus delta U plus delta E internal is equal to Q minus W. Okay. So what we're going to do is we're going to treat the bullet and tree as our system. So the system equals bullet plus tree. Okay. And with that in mind, the bullet nor the tree are going to change height. We're imagining that you're shooting the bullet into the tree essentially from point blank range, so that basically the bullet's not really going to fall any appreciable distance. So that's not going to change. So delta U is going to be equal to 0. There's going to be work done on the tree by the bullet and work done on the bullet by the tree, but both of those are internal to the system. So we'd expect the work to be 0 as well. Also, we don't expect the environment to have enough time to really warm up the bullet or the tree due to the sunlight or anything like that. So I'm also going to say Q is equal to 0. So ultimately what this gives us is delta K plus delta E internal is equal to 0. And that gives me that delta E internal, the change in internal energy, is equal to the negative of the change in kinetic energy. So delta E internal is equal to negative 1/2 mv final squared minus 1/2 mv initial squared, which equals minus 1/2 times 4.3 times 10 to the negative third kilograms times the final was 200 meters per second squared minus 1/2 times 4.3 times 10 to the negative 3 kilograms times 300.0 meters per second. Not quite the speed of sound, so we're not talking an AR here. But what we can do is we can say, I'm actually just going to do the 200 squared minus 300 squared, and then multiply that by the 4.3 times 10 to the third times 1/2, because they're obviously a common factor. So when I go 200 squared minus 300 squared, I get negative 50,000. And then that negative multiplied by a negative is going to be a positive. But now I'm going to multiply that times 0.5 times 4.3 e to the negative 3. And that gives me 107.5 joules. Notice a kilogram meter squared per second squared is a joule, because a kilogram meter per second squared is a Newton, but we have a kilogram meter squared per second. So that's a Newton meter, which is a joule. And if I look at this the 200 squared should have gave me 4 sig figs, which would be basically 5.000 times 10 to the fourth minus 9.000 times 10 to the fourth. So I still have 4 sig figs, and then I subtract them, and that should basically give me to the nearest 10th place. So technically the 7 and the 5 are not sig figs. So what that tells us is the question was, where did the bullet's kinetic energy go? Well, the bullet's kinetic energy went into the internal energy of the system. That means the individual molecules of the system, which means the molecules of the bullet and the molecules of the tree, actually had their individual energies increased, which you probably would know from everyday experience, even if it's not shooting a gun. Even if you just imagine something like hammering a nail. If you touch that nail right when you finish hammering it, it will be a little bit hot. Okay, and that's what's happening here. The tree got hot, the bullet got hot, the bullet got deformed, that changed some stuff. The bullet got squished to some extent, that forced the or the molecular distances from one molecule to the next to decrease. All that stuff spells internal energy increase, and that's what was transferred. So the energy was transferred only within the system, not exterior to the system. Any questions on that? All right, so that's how we navigate mechanical energy along with uh, internal energy. Now that we've got that, we're going to go into the part of thermodynamics it's kind of boring, but before you master this part, you can't do anything. So there's thermodynamic processes, and there's words that we use for thermodynamic processes. So let's do that by indicating some of these terms. I'm going to write them down, and then I won't write down the terms. You can see they're listed in your textbook as bold print, so you can copy those down to your notes yourself. I'm just going to write down the terms so you'll know them. So this is thermodynamic processes. These thermodynamic processes are isothermal. Anybody want to guess what that one is?
Say constant temperature.
Yep, that's constant temperature. And with constant temperature means delta T equals 0 for an ideal gas. Which implies delta E internal has got to equal 0. Okay. Now, delta T equals 0 doesn't mean the internal energy did not increase in general, but it does for an ideal gas because, as we said, an ideal gas, a monatomic ideal gas has E equal 3/2 in nRT or 3/2 in KT. If it was not monatomic, it might be 2/2 times nRT or 3/2 times nRT or 5/2 times nRT, so on and so forth. But the main thing is with ideal gases, the internal energy is a function of temperature. So in isothermal process, the temperature cannot change. That often is handled by putting something in contact with a thermal reservoir or what we call a heat sink. So for instance, if you got an object to like 20 degrees Celsius and you happen to find a really big lake that happened to also be at 20 degrees Celsius, then you could put that object in the 20 degree Celsius lake. And because the lake is so big, you could assume that the temperature of that object will be 20 degrees Celsius for a long period of time. Obviously, not seasons long, but at least, on the order of the normal time for an experiment. Okay. There's also processes that are called quasi-static. And isothermal means constant temperature. Quasi-static means so slow that each state is a series of equilibrium states. In principle, you can't really do it. You'd have to go infinitely slow, but it turns out that that's not too much of a daunting thing because quasi-static processes can actually take long periods of time and we still get fairly accurate results. So just know that quasi-static means a series of equilibrium positions, so that it goes literally from one equilibrium position, moves an infinitesimal amount to a new equilibrium position, moves an infinitesimal amount to a new equilibrium position, and so on and so forth. If that's the case, then you could actually graph it. You cannot graph non-equilibrium states because you don't have a single value of pressure or volume or temperature that accurately represents the entire system. Because the entire system has to be in equilibrium for all of those to be equal. So that's another diagram, but not quite. I mean, that's another process, but not so important as isothermal. That's why I did a single underline on that one. Also by this, you get that Q is equal to W. So those are two big conclusions for ideal gases in an isothermal process. Now, another process we're going to handle is adiabatic, and this is another important one. It's important, so I'll double underline it. So as I was saying, adiabatic is a process in which the system doesn't allow heat to flow in or out. Okay, so the entire system is basically isolated. You can imagine the system's in a calorimeter like I drew last time, and therefore no heat can escape and no heat can enter. That means Q is equal to 0 and delta E internal is equal to Q minus W, therefore implies delta E internal is just equal to the negative of the work done by the system. So that's some of the stuff you can find out. We'll later find out that there's another representation of P and V, like the ideal gas law, that can be used. Specifically, P1 V1 to the gamma is equal to P2 V2 to the gamma power in adiabatic processes. With ideal gases. Okay, so that's another important process. Now, adiabatic means no heat flows in or out. So one way you can accomplish that is by doing it really fast. Remember, for heat to actually be transferred, for energy to be transferred via heat, you've actually got to have individual molecules colliding with other individual molecules, and then those individual molecules have to go and spread their extra kinetic energy evenly to all the other atoms and molecules. So that necessarily takes a long period of time. So for instance, when you compress a air gas mixture in the cylinder of a diesel engine, you compress it from, say, like let's say 3 liters down to 0.3 liters, which is, typical, on the order of a power of 10 with a diesel. You have a compression ratio on the order of a power of 10, then it'll instantaneously explode without even a spark plug. That's how diesels work. And that explosion is an adiabatic process. Even though a butt ton of heat was created, that heat cannot flow from inside the cylinder to outside because it happens so quickly. So another process that we can go through instead of isothermal and adiabatic is isovolumetric. And you probably, by the clear words of that, can tell exactly what it is. That's another important one, so I'm double underlining it. But I'll give you the other name, and if I had given you this one, it might not have been so obvious. That's two words for the same thing. Isovolumetric and isochoric means one of constant volume. Okay. What we learn is that work is equal to the integral of P dV, and that implies delta V equals 0 implies work equals 0. So we end up getting delta E internal is just equal to the heat added. So that's another process that can happen. Anybody have any questions on that? There's one more I want to give you, and that's isobaric. Dang it, I keep writing with red. That's one of constant pressure. So in this case, work is equal to the integral of P dV, but P is a constant, so that becomes the integral of P dV, which equals P times delta V. So for this one, we see work is just equal to P times delta V for our isobaric process. Any questions on that? All right, now we've hit all the major processes we're going through here, and I want to show you basically where I got that work equals the integral of PdV. So what you can imagine in this case is imagine a cylinder like so. And imagine it's got a piston like so as well. Okay. Let's say this area in the bottom is a cross-sectional area A, and let's say that this piston actually moves up from where it is to this new spot. It moves up an amount dy. So work is equal to, or I should say dW is equal to F dot dl, which in this case becomes F dot dy j hat. Okay. Since it's a dot product, it's actually a scalar quantity, but pressure is equal to force divided by area. So force is just pressure times the area, and then that's multiplied by dy. But you see that that is A times dy, and this part right here is just dV. So you get dW is equal to P dV, or work is equal to the integral of P dV. So that's where that came from. Any questions on that?
I just want to double check with the isobaric one.
Mm-hmm.
That's B as in volume.
It's B as in boy.
No, I mean
V.
V, the delta
V
V
delta V
Oh yeah, gotcha. Yeah, that's a delta. Yes.
as in volume.
volume.
Yes. Yes,
Okay.
delta volume. Isobaric is constant pressure, so it's okay for the volume to change, whereas isochoric or isovolumetric is not okay for the volume to change. So if you considered an isothermal process, then you'd say work is equal to the integral of P dV, but you could use this isothermal process for an ideal gas. If you did that, then we know P could be replaced with nRT over V, and then dV. And since it's isothermal, the temperature is not going to change. The N is a constant for a fixed amount of gas, and the R is a constant. So I got nRT times the integral of dV over V, which ultimately gets work in an isothermal is equal to N times R times T times the natural log of V2 over V1. So that's a quick and dirty little calculation we can do to help us figure out the amount of work in an iso volume or in an iso thermal process. In an isobaric process, I worked one of those out. I worked one of the isothermal processes out. So we've gotten basically everything, and it's now time for your class to end. So we have essentially gotten up through section 19.7. So the test, the face-to-face test that we have, I'm probably just going to stick to the first two chapters, which is the exact same thing that the first the first online test is covering. So when you're taking that practice test, you're taking the practice test for that test as well as for the online test. So yes, Elizabeth, did you have a question? Or Ella?
No, she didn't.
No.
Okay, I thought she was raising her hand. So anybody else have any questions? You guys are free to go. I'll wait for the last person to leave in case anybody does have any questions.
I had a quick question.
Yes.
In the practice for chapter 18, we used a formula, the mean free path formula. Did we not cover that? Simply plug and chug.
Yeah, that's a more or less a plug and chug. There is one that used to be in there. I think it's still in the problem set where you had to sort of think through the process of the derivation. So it's not that trivial to do it, but it's an excellent example that I'll like y'all to do. I'm just never going to ask you that on a test.
Oh, so the mean free path probably won't even be on the face-to-face one.
It's definitely not going to, it's not supposed to be on the face-to-face or the online test.
Okay.
If you find one on there, make sure you let me know and I'll have to give you the points.
Yeah,
It
no,
was on the practice.
this is a chapter 18 practice, so that makes sense.
Gotcha. That's
All
cool.
right. Have a good day, Mr. Younger.
You too. See you guys. Anybody else have any
Professor,
questions?
Yeah, Professor, could you go over the adiabatic process? I kind of still, I'm not, I understand that there's no change in heat. But I suppose I kind of want to understand what's going on behind the scenes internally, why the gas explodes in the, in an internal combustion, what's really going behind there. I don't quite think I got, like, all the other ones seem to be fine. Just
Right.
the adiabatic seems to be a little, um, so essentially you reduce it down to the change in internal energy is equal to the negative of the work done by the system. So if the
Yes.
system does a bunch of work, the internal energy of that compresses if it does a bunch of work instantly, that does that changes the internal energy, which would change the state of the molecules. Is that what's going on? So
Yes.
the state, the phase state is phase state is linked to the internal and then so the work is that you're getting out of a car is tied to the instantaneous change in the phase state from vapor to liquid. Or
Yeah, it's that and the chemical bonding that goes on between the carbon atoms and the other, hydrogens and whatnot that are in the fuel itself.
Hmm.
So yeah, all that is it. But we say that's adiabatic because remember, you've got to choose the system, and the system we're talking about when we say it's adiabatic is the actual gas inside the piston. And an explosion occurs because when you compress it so much, that forces its temperature to go up. And that temperature exceeds the flash point of the actual air to gas mixture or air to diesel mixture. And that causes an explosion. Now that explosion generates more heat. That's the breaking of the chemical bonds and all that good stuff. That it creates more heat, but that heat is completely inside the system and it's coming from the internal energy of the system. And in fact, it will not leave the system because it doesn't have enough time to go out through the block of the engine.
Okay. So when the process happens greater than the overall cycle of the motor, it's considered adiabatic.
Exactly. Through that one stroke.
Okay. All right. I'm all on it, but all right.
Yeah. Well, it's kind of weird. You remember if it's after several of those strokes go by, you can see that it's not truly adiabatic. Clearly, some heat's going into it. It's just taking a long time for it to get there. So that's why the engine
Yeah.
ultimately heats up. But it's pretty darn close to adiabatic because it happens so fast.
Hmm. Huh. All right, I got them all on it.
No problem. Hey, there's some good books on the engineering of the internal combustion engine that I bought over the break. If you're interested in finding out more about that, just let me know. I can give you some titles. I found them for really cheap, like $5 on eBay.
I struggle with my normal schoolwork right now. You
Oh, you
know,
don't have time to just
Um,
do extra physics on the side? What's wrong with you?
no, man, it's. I mean, I am slow as molasses. You know,
Why are we even here, man? No, I get you. I
I
get
don't
you,
know.
Jerry. Let me know
All
if
right,
there's
take it
anything
easy,
else I can
Preston.
help you with.
All right, thanks.
All right, see you, bud. Bye-bye.